we will continue our discussion on microelectronic technology for MEMS. In the last lecture, already we have discussed on the deposition techniques, namely the evaporation, chemical vapor deposition and various kinds of evaporation techniques also. Today's lecture will continue on discussion on different topics like metallization, lithography, diffusion and ion implantation. All these steps are very much required for fabrication of microsensors and MEMS. Let us first discuss on lithography. Lithography, and sometimes it is called also photolithography, is a process by which we can transfer some pattern from photographic mask to a resultant pattern on a wafer. The transfer of any kind of structure from mask level onto the wafer level is known as photolithography. What is the technique? In photolithography process, a photosensitive polymer film is applied on silicon wafer. This photosensitive polymer film is known as photoresist. This film is dried and then it is exposed with the proper geometrical patterns through a photo mask to UV light or other radiation and finally developed. Instead of UV light, in some cases we use X-ray, electron beam or ion beam. Accordingly, those techniques are known as electron beam lithography or ion beam lithography or X-ray lithography. When you use UV radiation for exposing the film, then it is known as UV lithography. When you use deep ultraviolet rays, then it is also sometimes known as deep ultraviolet lithography. Now, depending on the polymer used, either exposed or non-exposed area of the film is removed in the developing process. That means, in some cases we will find that exposed portion of the film will soften and it will be dissolved in developer solution. In some cases, after exposure we will see that this polymer film, which is photosensitive, has been hardened and is very difficult to dissolve in developer solution. So, there are two kinds of photoresist, one is known as positive, other is known as negative photoresist. Now, the photolithography process requires various chemicals, gadgets and equipments. Those are namely photoresist, spinner, mask, mask aligner, developer solution, baking ovens, etc. So, photoresist are made sensitive either to UV light or electron beam or X-rays or ion beam. But out of all these lithography, ultraviolet exposure source is very much popular and UV lithography is very much used in most of the MEMS or VLSI process. Very few cases we require ion beam or X-ray lithography where we need high resolution and very small feature size, then sometimes we go for X-ray lithography or ion beam lithography. Now, as I mentioned, there are two kinds of photoresist, positive and negative photoresist. They are complementary to each other as far as their properties are concerned. Now, negative photoresist becomes less soluble in developer solution when they are exposed to radiation. On the other hand, positive photoresist becomes more soluble after exposure. In the diagram, the positive photoresist and negative photoresist behavior is shown. Now, you see the mask, there is a black portion here, this line is a mask, here similarly here the black line is a mask. So, here through that black portion the ultraviolet light cannot pass. Now, the blue color layer is substrate and the red is photoresist or any other film which is sensitive to radiation. Now, if you expose the side by side negative and positive photoresist, the photoresist coated substrate using the ultraviolet light with the same mask, then the pattern will be different. Now, here in the left side of the picture you can see when it is exposed. So, this portion, red portion will be exposed with ultraviolet light and this will be hardened, and unexposed portion will remain as soft, as a result of which after developing this portion photoresist will remove and we will get windows with a black region in the on the top of this particular window. Now, here in the right side same mask is used, where the exposed portion, for example, here and here the photoresist becomes more soluble and then it will be dissolved in developer solution, as a result of which you will get only this portion after development and exposure. So, thus we found that if we use positive photoresist instead of negative, we will be getting the structure which is complementary to the structure obtained in case of negative photoresist. So, what are the various steps in this kind of pattern transfer technique? So, the first step is preparation of the photo mask. So, photo mask making, that is first step. For that you have to have certain information which contains the geometrical feature corresponding to a particular mask, and that geometrical feature is electronically entered with the help of a layout editor software. There are various kinds of layout editor softwares are available. One such name is Lassie layout editor. You can design your pattern and electronically transfer onto a mask making machine. Then according to the data, the mask making machine will expose onto a emulsion or chromium coated substrate, or you can call it is a mask plate. So, depending on the data entered into the pattern generator, the mask plate will be exposed, and after that if you develop those mask plate, then you will be getting the structure on that particular chromium plated or emulsion coated glass plate, and your mask will be made. In some cases we initially prepare the reticle of the mask, and then by step and repeat camera we can duplicate those pattern in multiple numbers, so that you can get at the same time maybe thousands or millions of chips will be exposed on the same wafer. So, in VLSI process, first you generate the reticle means single chip mask, then that is repeated in different camera which is known as step and repeat camera, and then you can have the full mask which contains millions of chips. So, first step of any kind of pattern transfer is to make the photo mask. After making the photo mask, then you go for pattern transfer onto the wafer. Now, step 2 is that transfer the pattern from the mask plate onto the substrate. It uses spinner, photoresist, exposure tool, developer solution and sintering oven. And step 3 is a alignment and exposure. In case of microsensor or MEMS devices, we sometimes require lithography on both sides, with the top side and bottom side, because sometimes we want to etch certain windows with respect to some structure at the back, or on the other hand we want to open some windows at the back side of the wafer with respect to certain structure in the front side. So, this kind of alignment and lithography is not required in case of VLSI fabrication, but in case of microsensor fabrication we need this kind of double sided alignment technique. So, you have to use a different kind of mask aligner machine which is known as double sided mask aligner machine, so that you can align either front side or back side with respect to the other to create certain microstructure for your specific application. So, that here some difference is there so far as VLSI lithography is concerned. Now, next step will be developing. After exposure of the film you have to develop, just similar to the photographic plate developing. So, you develop, then during developing either the soft portion or the hard portion depending on which kind of photoresist you are going to use. So, that will be dissolved and then you will get the pattern, and after getting the pattern then you sinter whole thing, then you go for etching to create certain windows or the structure finally. So, that is the total the transfer process from mask level onto the wafer level. Now, this is a pictorial diagram using both positive and negative photoresist to get the pattern from mask level to the wafer level. So, here you can see here the first is silicon wafer, on top of that silicon dioxide, and on top silicon dioxide we have coated with photoresist. Now, this is a photoresist, then silicon dioxide, bottom is a silicon. Now mask plate is aligned onto the photoresist film, and on the mask plate you can see this portion is a black and rest of the portion is opaque, transparent, and this is the opaque. Now, through the black region which is opaque, the ultraviolet light cannot pass, and through the transparent region it will pass. So, now if you use positive resist or negative resist, then the structure will be different. Now, you can see the positive photoresist case where you the transparent region, particularly this portion, when it is exposed. So, this portion the photoresist will be softened, and in the developer solution this portion photoresist will be removed, and only the black region, this particular region photoresist will remain. On the other hand, if you use negative photoresist, so under exposure of ultraviolet light, this portion to this portion to this portion, it will be hardened. So, here it is hardened, and only the black region the photoresist will not be exposed by ultraviolet light. As a result, here it will remain as soft, and in developer solution this particular region photoresist will dissolve. Okay. Now, so in positive resist in the same mask we will get this structure, in negative resist in the same mask we will this kind of structure. Now, what is the next step? Next step is to etch the film. So, now during etching the silicon dioxide, because this particular region it is covered with silicon dioxide and silicon can be etched here, it is covered with photoresist, then silicon dioxide can be etched here. Similarly, here this is the silicon dioxide, the red region is the silicon dioxide. So, it is a photoresist. So, now through the photoresist window you can etch silicon dioxide only this portion, as a result of which you can get windows here on silicon. Similarly, here the complete silicon dioxide film will be etched, and the covered region the silicon dioxide will remain. So, in the same structure, if you go for positive or negative, the similar such kind of pattern you will get after development and etching. Okay. Now, the steps of lithography are shown here along with the justification. In some cases we found that because of the inadequate surface, inadequate quality of the silicon dioxide or silicon surface, the photoresist will not properly adhere to the substrate. In that case, you have to use some adhesion prompter. So, adhesion prompter helps to properly adherence with the photoresist film and the silicon or silicon dioxide film. So, it is very important, because until unless the photoresist adherence with the substrate is not proper, so in the subsequent process photoresist can peel off. So, then you cannot go for the complete etching or developing steps. So, you have to ensure that photoresist will adhere properly on the silicon dioxide or silicon surface, and this is very important. As I mentioned why it is important, and this kind of problem sometime you can face if the oxide quality is not good and oxide is contaminated or the substrate is not properly cleaned So, in that case the adherence will be poor. Some remedies are there. This adherence problem is much more severe if you go for a very fine line lithography. If you go for resolution of 1 micron or submicron kind of structures, then if adhesion is not 100% perfect, then there is a problem of seepage of the developer solution to the side of the photoresist film, as a result of which structure will not be according to your design and the resolution you will not get. So, in case of the designing of micron or submicron kind of structure, the adhesion prompter is very much essential, and one of the adhesion prompter is HMDS. So, HMDS film initially coated on silicon dioxide surface, and then you go for spinning photoresist. So, after the resist application, and that is the technique is dispensing and spinning. That means dispensing means you just put the photoresist enough amount of photoresist on the surface of the silicon dioxide, then you spin the silicon wafer. Spinning is required to get uniform photoresist thickness. So, if you spin up, photoresist material is a liquid material. If you put that enough amount of liquid on the surface of the wafer, then you spin it suddenly with a certain speed, and that speed is nearly 3000 to 4000 rpm, then you will find the thickness of the photoresist film over the entire wafer will be uniform. Why you need uniform? The reason of or the requirement to uniformity on the thickness lies uniform exposure, because if you see during exposure the ultraviolet light will react with the photoresist film. Now, if the photoresist film thickness is different, the time required for complete reaction will be different at different region. Where thin photoresist film, so reaction will be completed very fast. Where the photoresist film thickness is more, then the time requirement for complete reaction, that polymerization, that is known as polymerization, will be more. So, as a result of which the some portion will be developed very fast and some portion will not be developed where the reaction is not completed. So, because of that we need the uniform thickness photoresist film, so that uniformly and equally over the entire surface of the silicon the reaction will be completed, so that the in developer solution and the same time the structure will be developed. Non-uniform thickness of the photoresist will lead to non-uniform the structure appearance on the surface after development. In some cases the structure will be much more prominent, some cases it is not prominent. So, after that you are drying the photoresist, and why you are drying? To remove the solvents, because it is a liquid. Why liquid? Because you have to spin, and if it is not liquid you cannot spin on the surface. So, after spinning, the solvents are removed by drying the photoresist. Next step is a resist pre-bake. That drying means when you are spinning, automatically the solvents will be evaporated. After that pre-baking, at certain temperature you have to pre-bake the film to harden and improve the adhesion. Okay. Next step is expose, and where you defines the image in the resist. After that is resist develop, which removes unwanted resist. So, in developer solution what will happen, as I mentioned, that soft region will removed wash away in the developer solution and hard region will remain. So, that removes unwanted resist in developer solution. After the resist post bake, when you are developing, then again you are putting the whole thing in the liquid. So, those developer solution will be there on the surface of the photoresist as well as substrate, and some of the developer solution will be absorbed by the film. So, as a result of which the film, photoresist film will be soft, and again you have to dry it before going for actual silicon dioxide etching. during that drying, which is known as post baking, again the photoresist film will completely adhere on the substrate. So, that will improve adhesion. After that you etch the oxide, and here you have to see resist must not react with the etch or peel from the surface. When you are etching silicon dioxide, then the protected silicon dioxide should be ideally protected. That means, on that silicon dioxide there is a film of photoresist, and the etching solution of the silicon dioxide should not react with the photoresist, or in that solution, which is in case of silicon dioxide is buffer hydrofluoric acid, you know the buffer hydrofluoric acid will not react with the photoresist, or it will not help the photoresist to peel off. So, that we have to be ensured. Now, after developing is completed, then post baking is done. Next step is resist removal. So, then developing completed, photoresist post bake, and then oxide is etched, and after oxide is etched, then the job of the photoresist passivation is over. So, this protection layer is not required. Then you have to remove the resist, and that removal is done with the help of either oxygen plasma or hot acid, and that hot acid sometimes in case of negative photoresist we use H2O2 and H2SO4 1:1 ratio, which is known as a Carrot's acid. In case of the positive photoresist we used acetone, hot acetone, or sometimes it is used is special photoresist remover solution from the photoresist supplier. They can give some they also specify some chemical for photoresist removal, or if you go for dry removal, then you can go for oxygen plasma, and that also etch photoresist. So, this is the complete steps along with the justification. Now, there is another kind of photolithography technique which is known as lift off technique. So, lift off technique is a special technique where you do not require the etching solution of the film. So, in some cases we may not know the etching solution. For example, if you are going to design or pattern a tungsten film or molybdenum film or some other say ceramic film whose etching solution is not known, but you want to pattern it. So, in that case the ideal technique is to use lift off technique, and lift off technique is totally different. Here what we do, we pattern the photoresist instead of in normal photolithography. First we deposit the film, or in case of silicon dioxide we grow it, or in case of metal we first deposit metal and then we coat photoresist, then we go for patterning. But in case of lift off technique we do not deposit film or grow silicon dioxide, first we coat with photoresist and we get the pattern, then we deposit film. That means photoresist is first deposited for photomasking and pattern, and then metal film is deposited and lift off technique follows with initial photomasking. Okay. So, let us see in a picture what is the difference in this picture, what is the difference between normal photolithography and the lift off technique photolithography. So, normal photolithography is known as the subtractive method, and lift off technique is known as the additive method of pattern transfer. So, subtractive method means here what I discussed in earlier view graph, that film substrate, then this is the mask, then this film is for example the mask is a photoresist and the film is say silicon dioxide for example. So, now the mask, then here you can etch the silicon dioxide, then what you do, you can remove the photoresist, you can get the pattern. This is the silicon dioxide pattern. Okay. Now, this is a normal, but in case of additive what we do on the substrate, instead of depositing film we first deposit mask. What is the mask? Means photoresist. You can see the difference here. First film, that film may be either aluminum in case of metal or in maybe silicon dioxide. So, we have coated first, but here what we did, first it is coated with photoresist and then on photoresist we pattern it, and after that we deposit the desired metal or silicon dioxide. Not initial silicon dioxide, then photoresist. First photoresist is deposited, then pattern, then we deposit it, we deposit the either metal or silicon dioxide here. That is the film. Now what we do after this, we just dip the structure into a photoresist removal solution. So, if you dip the whole thing in photoresist removal solution, what will happen? You can see here here develop a solution or the photoresist remover solution, I should say. The photoresist remover solution will remove photoresist from this portion, and from this region it will react, the photoresist remover solution will react with the photoresist here and here, as a result of which photoresist in this region and this region will dissolve, and this two portion will be floating, and that will go away, and you will get the structure here. So, both the cases we got the same structure here, but in this particular case you need the etching solution of the film, but in this particular case we do not need the etching solution of the film. So, this lift-off technique is used in some cases where the etching solution is not known, or you know the etching solution, but that etching solution will react with the photoresist film. If that etching solution react with the photoresist film, in that case also photoresist will not protect the surface. When you are going to etch the film here, so then here you say photoresist will be reacted and film also will be reacted, then whole thing washed away. So, but here if you need some solution which can react, which can dissolve the photoresist, but not the film. So, that is in normally used the positive photoresist, and in that case positive photoresist remover solution is acetone. So, here after this step you just dip the whole thing into the hot acetone. So, acetone will remove the photoresist and you will get the structure here. But here one limitation is there. What is the limitation? Now, you can see from the diagram, the photoresist will react only through this portion or this portion. Now, if I use the thickness of the mask, means photoresist film is very small, so that this portion is because this is very low. So, this portion will be nearly here. So, there is no chance of attacking photoresist from this side or this side. So, in that case the photoresist will not be removed. So, one condition you have to satisfy. What is that condition? The film thickness should be smaller than the photoresist thickness. This is the film thickness, the red region, it should be smaller than the mask, means photoresist thickness. Okay. So, that means thickness of the photoresist should be large, otherwise this sort of large compared to what? Large compared to the film thickness. So, otherwise you cannot go for the lift-off technique. So, if you can get thicker photoresist film, for that you have to use a special kind of photoresist, positive photoresist, whose viscosity is more, and by which you can pattern larger thickness resist. Okay. So, this is one condition. If you satisfy, then easily you can pattern without knowing the etching solution of that particular film. So, this is very much used in many cases of pattern transfer. Now, next step is the metallization. So, metallization requires, after completion of fabrication of the individual devices, that means if you fabricate say some resistance, or you can fabricate some transistors or diodes, then at the end you need interconnection of these components or devices. For that you need a metal film, and metal film is etched, and as a result of which you can get the interconnect lines. So, now when you go for metallization, there are certain thumb rules to select the metal film which will be suited for your application or your device. What are those points? Number one is low resistivity or high conductance, easy to form. What does it mean? Obviously, the metal lines are used for interconnection or contacts. So, its resistivity should be low. If it is not low, then what will happen? So, total interconnect line will give you certain resistance, and that resistance will be parasitic, I can say, and that will reduce the speed of your circuit, because additional resistance is coming into the picture, which is not desired. So, in high speed circuit or any of the VLSI circuit, which the metal lines are required only for interconnect. So, their resistance should not be incorporated. So, low resistivity should be there, that means high conductance, and easy to form. Easy to form means that metal film can easily pattern. That means there are certain metal film by lithography you cannot get the pattern. One such is, say, copper, but you have to go for certain metal film, so which can be easily patterned by conventional lithography and etching technique. For example, gold, aluminum are most choiceable material for metallization or any integrated circuits or VLSI. Low contact resistance and non-rectifying contacts. So, metal films are used for contacts also. So, the contact, that means the silicon and metal contact, so that must be ohmic, non-rectifying. If it is a rectifying contact, then at the contact position you are unintentionally fabricating some diodes, which is metal semiconductor junction diode. So, metal semiconductor junction should be ohmic for ideal contact. Okay. So, that all the metals with silicon will not give you ohmic contact, some of the metal combination with silicon give rectifying contact. So, when you will select a material, you have to take care of that aspect. So, the contact must be ohmic, so that you can choose the proper material. Others is the low contact resistance, because in VLSI or even in MEMS devices the contact windows are very small, and in some cases you go for, say, even 5 micron by 5 micron contact, in some cases 10 micrometer by 10 micrometer contact. If you go for ULSI devices, the contact windows are getting more and more smaller, much more smaller. So, in that case, if it is a small, it will introduce some contact resistance, and that contact resistance should be as small as possible, otherwise additional parasitic resistance are coming into the circuit. So, that you have to shaped and controlled as required. That means, what does it mean? Your metal film which is being used for metallization must be shaped, means it will be lithographically compatible. So, that metal film can go for lithography process, and it will be patterned using conventional lithography, that is shaped and controlled as required. Has mutual solubility with silicon, that is another aspect. So, if that metal film does not dissolve into the thin layer of metal, you will not get proper contact. Mutual solubility with silicon, that means at the interface the metal and silicon will form certain alloy, that is mutual solubility, otherwise contact will not be proper. It is very important aspect when you are selecting a material. Okay. Next is penetrates thin native oxide. When you deposit metal film on silicon, then always bare silicon you will not get it, and a native oxide will be there. Even you clean the wafer and then go for buffer hydrofluoric acid dip. So, when you are transferring the wafer into a vacuum chamber for deposition of metal film, during that period a thin layer of native oxide may be in the range of 2 to 3 angstrom unit. So, that will be formed, and that native oxide is very difficult to remove from the silicon. So, on top of that you are depositing aluminum. So, that means aluminum must penetrate through that native thin film of oxide, otherwise if it cannot puncture, you will not get good proper ohmic contact. So, the metal film which you are selecting for metallization must penetrate through that thin layer of oxide. Next is the mechanical stability, good adhesion and low stress. Good adhesion is obviously required. Low stress, that means you are depositing metal film on silicon. So, silicon, the metal, and this metal film will run on silicon dioxide. So, that means silicon dioxide, silicon and the metal, that must produce low stress, because subsequently if you go for high temperature step for annealing. So, then after annealing, when you are cooling down, so if there is no compatibility on the thermal expansion coefficient, so a stress will be developed, and if a stress develops, so the in metal film in some bump may create and you will not get proper contact there. Okay. So, because of the stress, so the metal film can bend and it can peel off from the surface. So, that you have to take care. So, that means low stress is desirable, mechanical stability should be high, because when you are patterning say 100 or 1000 microns or millimeter length and width is of the order of say 5 micrometer to 10 micrometer, then these narrow lines in subsequent process must be mechanically stable. So, during subsequent processes those lines should not come out from the silicon surface. So, that is mechanical stable, means it will not only adhesion, it should not, there should not be any crack on the lines. So, there should not be any discontinuity in the line. So, that means mechanical stability is highly desirable. Metallurgically compatible with silicon, other metals and passivation. Metallurgically compatible means it will form with that proper alloying with that silicon or other metal. For example, in multi-level metallization or multi-layer metallization, sometime you deposit gold on chromium, sometime in between chromium, gold or aluminum you can use the titanium as a diffuser layer. So, that means with titanium and gold it must be metallurgically compatible, that means it may form the layer by layer, it will show its own identity in the multi-layer environment. So, those are known as metallurgically compatible. So, next point, it should not contaminate wafers or working apparatus. The metal which you are selecting should not contaminate the wafers or working apparatus. Okay. Next point is minimal junction penetration and low electromigration. So, the metal film should have low electromigration. What is electromigration? If you apply field, electric field, then the metal molecules or atoms should not migrate, because electric field will be high, because in VLSI metallization, if we even if you use say 1.2 volt supply or 5 volt supply, so if the lines are very narrow, so field developed in one end to other end of the metal line will be very high. If it exceeds 10 to the power 6 volt per centimeter, then there is a possibility of migration of the molecules. In case of aluminum metallization, aluminum molecules will separate from each other. So, as a result of which there a chance of open circuit into the line, and those aluminum particles after migration, if it falls on nearby metal line, so there is a possibility of short circuiting of the first metal line in the never metal line. So, due to the migration of the aluminum molecule, both open circuit and short circuit is possible. So, that you have to take care of. Another is minimal junction penetration, that is very important if you go for shallow junction devices. If the aluminum penetrates to the silicon, because aluminum dissolves in silicon and it goes into deeper layer into the silicon, it may short the shallow junction. If the junction depth is not very high, there is a possibility of shorting the junction. So, that also you have to take care of. That means, there are a lot of points which you have to take care of when you are selecting a certain metal for metallization. Okay. Now, what is the technology of metallization? There are various kinds of methods used. One is resistive heated evaporation, that I have already discussed in the first lecture of the microelectronic technology for MEMS. Various kinds of resistive heated evaporation is being used, that is you see the different kind of filaments are used, that already I have discussed. Electron beam evaporation I have discussed, inductively heated evaporation I have discussed, sputter deposition and CVD. All these techniques which are used for film deposition, means say silicon or polysilicon or oxide film, the same techniques are being used for deposition of metal films also. All the deposition process require vacuum chamber. Okay. Now, I will discuss on diffusion. So, diffusion in silicon is done from three methods. What are the three methods? Diffusion from a chemical source in a vapor form at high temperature, diffusion from a doped oxide source, diffusion and annealing from an ion implanted source. These are the three techniques which are used for diffusion of impurity into the silicon. And there are two kinds of diffusion. One is known as diffusion from a constant source, which is known as constant surface concentration diffusion, and diffusion equation you know the fixed law that if you solve in this particular situation, that means constant diffusion from a constant source, then you will get the solution n x t is equal to n s complementary error function x by 2 root dt. So, constant surface concentration diffusion means the at the surface the supply of the dopant atoms will be infinite. So, continuous supply is there. So, that surface concentration will be constant at the surface. Then if you increase temperature and time, time is small t and temperature lies in d, d is the diffusion constant, is a function of temperature, and small t is the time. So, total deciding factor is d and t product. So, dt product if you increase, so the impurity atoms will diffuse more and more, and if Nb is the background concentration, if you diffuse for longer time, then the junction depth will be more and more. So, this is dt under root dt is 0.15 micron, you can get junction depth nearly 1 micron. If it is a 0.2 micron, junction depth you are getting nearly 1.4 micron. If it is a 0.25 micron, the junction depth you will get nearly 1.6, 1.7 micron. That is more means two way you can increase product of dt. One is you can increase the time, and another you can increase the temperature. If you increase the temperature, then capital D will also increase. Okay. So, this is a function of temperature, and this complementary error function diffusion, we use the error function, and error function is defined by this equation, and the value of the error function is found is not a closed loop formulae. You have to search some tables or curves to find the error function value. Okay. If you know the error function value, you put it here and you can get the doping concentration at different x values, and the complementary error function profiles are like this. There is another kind of diffusion which is known as constant total dopant. So, constant total dopant means at the surface of the silicon the supply of dopant atoms are not infinite. A fixed amount of dopant is supplied, then you cut the supply of impurity atoms. So, as a result of which, what are the constant dopant lying on the surface, those dopants will go gradually into deeper into the silicon layer, and as a result of which surface concentration which goes down. That you see initially the surface concentration is here and the supply of dopant atoms is fixed. So, if you go for longer diffusion, either you can increase the temperature or longer time, as a result of which the dopant atoms will go much more deeper into the silicon, as a result of which surface concentration goes down. Again, if you go for further diffusion, that means you see the root over dt, that is 0.1 micron to 0.5 to 1 micrometer. That means if you increase a t much more, then surface concentration further goes down, but as a result of which the junction depth you will get larger and larger. This kind of profile is known as Gaussian profile, and basically it is a half Gaussian. So, this is sometimes known as limited source diffusion or Gaussian diffusion. And here if you solve the fixed law, the doping concentration is given by nxt is equal to q naught by under root pi dt, where q naught is the total given by is a total dopant at the surface, and which is constant as far as limited source diffusion is concerned, and q naught is given by twice n naught under root d1 t1 by pi, and n naught is the surface concentration at pre-deposition. Now, both error function and Gaussian profile depend on 2 under root dt, means 2 multiplied by under root diffusion length. dt product is sometimes known as a diffusion length, and Q naught is the total integrated dose, that is number of impurity atoms per unit area. So, these are the two kinds of diffusion. Normally, in normal diffusion technique, we use two step diffusion. One is known as pre deposition diffusion, other is known as the drive in diffusion. So, free diffusion is controlled by error function diffusion, and drive in diffusion is controlled by the Gaussian profile. Now, typical diffusion profile in a particular transistor is like that. This is the emitter region. So, N plus diffusion, this is the base region P diffusion, then it is the epitaxy N epitaxy, then buried layer N plus. So, this is the typical doping profile in a NPN transistor. In this side, a bubbler arrangement is shown, through which you can just push dopant atoms into a bubbler, and then the dopant atoms in the form of gas, and it is flown into the tube. So, that for example, if you go for the phosphorus diffusion, one of the liquid source is POCl3, this POCl, phosphorus oxychloride. So, then raw phosphorus oxychloride is not enter into or is not passed through the tube, which we do normally. Some carrier gas is used, which is nitrogen. The nitrogen is bubbled through this POCl3. So, POCl3 vapor along with the nitrogen, that it flows into the chamber, and there silicon substrates are kept, and the POCl3 will react on silicon. Ultimately, phosphorus atom will come out, and that phosphorus atom will go into the silicon. So, this kind of the bubbler arrangement is used for incorporation of dopant vapor into the diffusion tube. So, now next step is the ion implantation. That is another kind of the another technique by which you incorporate dopant in a controlled manner. So, ion implantation is a process of introduction of ionized projectile atoms, which we call impurity, into targets, and the targets here is silicon substrate, with enough energy to penetrate beyond surface region of a single crystal substrate in order to change its electronic properties. That is the definition of ion implantation. And how it is done? First, the dopant atoms are vaporized, then they are accelerated, and then directed at the silicon substrate. Therefore, there are three steps. The dopant atoms are first vaporized, it has to be in vapor form, then it has to be accelerated. So, the energy of the impurity atom will increase. So, after acceleration, then they are focused and directed towards the silicon substrate, where it will colloid into the substrate, and it will go deeper into the silicon. That is a physical bombardment process, ion implantation. Dopants enter the crystal lattice, colloid with silicon atoms, gradually lose energy, finally coming to rest at some depth within the lattice. That is the process. First collision, it will lose energy, and after losing energy, it will settle down at a particular depth on the silicon. That is the steps. Now, what are the specific features of ion implantation? You can get precise control over the number of implanted dopants. The control of impurity in ion implantation is of the order of plus minus 1% over the range of doses 10 to the power 10 to 10 to the power 17 ions per centimeter square, but in diffusion at best 5 to 10% at high concentration, and watts at low concentration is achieved. That means, what is that? You can get the control of impurity atom plus minus 1% in case of ion implantation. In parallel, you can see in case of diffusion the control is 5 to 10%. So, much more precise doping profile, much more control on the dopant atom is possible in case of ion implantation. What are another aspect is a low temperature process. Ion implantation is a low temperature process. It is done below 400 degree centigrade, where diffusion is a very high temperature process. Normal temperature range is 900 to 1100 or 1150 degree centigrade. And nowadays all VLSI process people prefer low temperature because of the out diffusion of impurity, because of the problem of rearrangement of dopant atoms, and further diffusion which will change the doping profile, that people try to get rid of, and as a result of which low temperature process is highly desirable, and there ion implantation is one of the choicest method of incorporation of impurity atom into the silicon. And wide variety of profiles can be obtained by controlling energy and dose, which is not possible in case of diffusion. Different kinds of profile you can get by controlling energy and dose. I will show you some doping profile, diffusion profile curves in ion implantation, which will show you how the various kinds of doping profile you can achieve. Ion implantation is a non-equilibrium process. What does it mean? That means it can introduce impurity atom in excess of solid solubility, which is not possible in case of diffusion. Diffusion maximum dopant incorporation is up to its solid solubility limit, beyond that you cannot do it, but in ion implantation you can do it. The impurity atom may exceed solid solubility limit, that is why it is known as a non-equilibrium process. Diffusion is not a non-equilibrium process. Other points are also there. Implantation is conducted in vacuum, so you can expect a clean and dry process. Diffusion is not in vacuum, in normal atmosphere, so there is a chances of incorporation of dopant impurity atoms other than the dopant atoms. So it is a clean environment, clean process in ion implantation. Next point is implantation energy rises from 1 keV to 1 MeV, resulting in ion distribution with average depths ranging from 100 angstrom to 10 micron. You can get 100 angstrom depth, diffusion depth, which is not possible in case of diffusion, by controlling energy. So low energy ion implantation of the order of 1 keV, 2 keV, 5 keV, you can have very shallow depth junction. So nowadays shallow diffusion are all made by ion implantation, it is not possible in diffusion. On the other hand, if you use high energy ion implantation in the range of 1 MeV, you can get higher depth. So in SOI device, they are silicon and insulator devices. So normally high energy implantation is required, those kind of things you cannot get in case of diffusion. Okay. So doses range from 10 to the power 12 ounce per centimeter square to 10 to the power 18 ounce per centimeter square. So dose basically gives you the resistivity value. Energy gives you the junction depth, how much deeper you can implant the dopant atoms, and concentration, which gives you the resistivity or conductivity of the layer, will be decided by the dose. So it can range from 10 to the power 12 to 10 per centimeter square to 10 to the power 18 ounce per centimeter square. But only one drawback in ion implantation, what is that? It results in damage to the semiconductor, but its solution is also there. What is the solution? Annealing at elevated temperature is necessary to heal some or all of these damages. So that is why ion implantation is followed by annealing, because during implantation some minor damages will be created and those damages will be removed by annealing technique, which is solid phase epitaxy. So during the implantation process, because of the damage, the material may be amorphous in nature, and how do you know it? Just after implantation, if you go for the measurement of the seed resistance, you cannot measure because it is amorphous in nature. But after annealing, it will be recrystallized, so easily you can get the single crystal layer, and then you can measure the seed resistance by 4-point resistivity method. Okay. So that is one of the reason, just implantation, if you go for measurement of seed resistance by 4-point resistivity method, you cannot measure it. Okay. So what are the different ions used in case of ion implantation? These are shown here. In case of p type dopant in silicon, we use the boron or Bf2 ion. For n type in silicon, you use phosphorus, arsenic and antimony ions. In case of gallium arsenide, for p type dopant you use zinc and cadmium. Gallium arsenide n type we use silicon and sulfur. Typical energy in ion implantation is 10 keV to 500 keV. Typical ion current we use 10 microampere to 10 milliampere. This is the ion current. Typical dose we use 10 to the power 11 to 10 to the power 16 ions per centimeter square. And this particular picture shows that how the profile changes for different implantation energy. You can see here 30 kV, 100 kV, 300 kV and 800 kV boron is implanted into silicon. So, if you use 30 kV, the profile looks like this, 100 kV profile looks like this, 300 kV profile looks like this. So, that means if you want 300 kV, so from the surface also you will not get the impurity atom, here also no, you are not getting. So, in the middle of the wafer you will get profile like that. If you want the Gaussian profile at a particular depth of the silicon, then go for 100 kV, there you will get the profile like this. So, that means subsequent implantation if you go, so then you can get a profile like this it will come if you combine all these things something like that. So, that means by controlling energy and dose you can have any arbitrary profile in case of ion implantation, which is not at all possible in normal diffusion techniques. Okay. So, the annealing is must in case of ion implantation for removal of damage and for recrystallization, as I mentioned, restoration of electrical activity, because mu, sigma, eta all will be restored after annealing. Then furnace annealing causes appreciable redistribution of impurities. So, people prefer for RTA, which is a rapid thermal annealing, and it is suitable for shallow junction. Two kinds of annealings are there, one is furnace annealing and is a rapid thermal annealing. So, furnace annealing cause again redistribution of impurities, but if you use RTA means high temperature, very small time, maybe 1 minute, maybe 45 seconds you can use for annealing at high temperature, say 800 or 900 or 1000 degree. So, that will heal up all damages and again it will recrystallize, and that is the preferred ion implantation followed by rapid thermal annealing. Now, in conclusion of in ion implantation we can say implantation is an indispensable technique in VLSI fabrication. Ultra-shallow junctions for deep submicron CMOS and BiCMOS technology, RTA is essential. High energy, high dose oxygen nitrogen implants are required for SOI fabrication. Recent trend is low energy, high dose and low temperature implant for the submicron VLSI ICs. Let us stop here today. So, next class we start micromachining of silicon, and first step is the etching of silicon. We will discuss in the next lecture. Thank you.